Hackers and hackerettes, welcome to a new video in our learning path. If you don't know what this is, then you're probably missing a lot of context. So I recommend you start by watching my playlist on YouTube called TryHackMe Pre-Security Network Fundamentals, because this is a series that builds on top of each other. And yeah, without further ado, if you're coming back, welcome back. Let's get into introducing LAN topologies. LAN stands for local area network, which means your local network that you have in your home, which is like your phone and your PC or your laptop, your whatever, all connected to the router and so on. So over the years, there has been experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we're actually referring to the design or look of the network at hand. Let's discuss the advantages and disadvantages of these topologies below. So the first one we have is the star topology. The main premise of a star topology is that devices are individually connected via a central networking device, such as a switch or a hub. This topology is the most commonly found today because of its reliability and scalability despite the cost. So this is probably what you have at home, like every individual device is connected to some kind of central device, let it be a router, a switch, or whatever it is. So this is called a star topology, and you can see why it is called that. Any information sent to a device in this topology is sent via the central device to which it connects, like the router. Let's explore some of these advantages and disadvantages of this topology below. Because more cabling and the purchase of dedicated networking equipment is required, it is more expensive than any other topologies. However, despite the added cost, this does provide some significant advantages. For example, this topology is much more scalable in nature, which means that it is very easy to add more devices as demand for the network increases, which is true. Like you can have like the maximum connected to the router, like the maximum connected devices. You can essentially just replace a single device with a switch, which gives you more devices to connect to, and then the switch is gonna connect to the router and so on, and you could just scale off of that. Unfortunately, the more the network scales, the more maintenance is required to keep the network functional. This increased dependence on maintenance can also make troubleshooting fall so much harder. Furthermore, the star topology is still prone to failure, albeit reduced. For example, if the centralized hardware that connects to the devices fails, these devices will no longer be able to send or receive data. Thankfully, these centralized hardware devices are often robust. So yeah. Your router, your switch or whatever, these are like devices that have been perfected over the years, and they are pretty reliable. So most likely, whenever you are having internet problems, it's your ISP and not your router. But I say most likely because, you know, because that is most likely. There is still the like faulty cables, or the router is just dying or whatever. So yeah. Next we have bus topology. This type of connection relies upon a single connection, which is known as a backbone cable. This type of topology is similar to the leaf off of a tree in the sense that devices' leaves stem from where the branches are on this cable. Because all data destined for each device travels along the same cable, it is very quickly prone to becoming slow and bottlenecked if devices within the topology are simultaneously requesting data. This bottleneck also results in very difficult troubleshooting because it quickly becomes difficult to identify which device is experiencing issues with data all traveling along the same route. So you can see what we're talking about right here. So essentially you have like a main wire or a main connection, and then off of that you get like multiple devices. So from this you do not have like a central router or anything, but you do have this main connection right here. However, with this said, bus topologies are one of the easier and more cost-efficient topologies to set up because of their expenses, such as cabling or dedicated networking equipment used to connect these devices. Lastly, another disadvantage little redundancy in place in case of failures. This disadvantage is because there is a single point of failure along the backbone cable. If this cable were to break, devices can no longer receive or transmit data along the bus. Yeah. Then we have the ring topology, also known as token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop, meaning that there is little cabling required and less dependence on dedicated hardware, such as within a star topology. So right here, we're talking about like a local network, by the way. So you can see that they are all connected to each other. But for example, if you're on this and you want to reach here, you can see where the problem is. You have to pass by this or whatever. A ring topology works by sending data across the loop until it reaches a destined device, using other devices along the loop to forward the data. Interestingly, a device will only send received data from another device in this topology if it does not have any to send data or to send itself. If the device happens to have data to send, it will send its own data first before sending data from another device. Okay. Because there's only one direction for data to travel across this topology, it is fairly easy to troubleshoot any faults that arise. However, this is a double-edged sword because it isn't an efficient way of data traveling across a network, as it may have to visit many multiple devices first before reaching the intended device. Lastly, ring topologies are less prone to bottlenecks, such as within a bus topology, as large amounts of traffic are not traveling across the network at any one time. The design of this topology does, however, mean that a fault, such as a cut cable or broken device, will result in the entire network breaking. Yeah. So what is a switch? Switches are dedicated devices within a network that are designed to aggregate multiple other devices, such as computers, printers, or any other networking cable device, using Ethernet. Ethernet is the cable, the internet cable that you connect. So modern days, you have a router and a switch all in the same device. But previously, you had a dedicated router and then dedicated switches. So the switch, all of it did, like all the thing that it did was essentially connect multiple devices to it. And then from it, you'd connect it to the router. So the router can only talk to the switch or multiple switches. And then switches were to switch data internally in the network. But in modern days, the router and the switch are usually just one device, which is your most common like connection from the ISP. These various devices plug into a switch's port. Switches are usually found in larger networks such as businesses, schools, or similar sized networks where there are many devices to connect to the internet. Switches can connect a large number of devices by having ports of 4, 8, 16, 24, and 32, and 64 for devices to plug into. Yeah, so it just allows you more output or like more devices to be connected to the same network. Switches are much more efficient than their lesser counterpart, hubs and repeaters. Switches keep track of what device is connected to which port. This way, when they receive a packet, instead of repeating the packet to every port like a hub would do, it just sends it to the intended target, thus reducing network traffic. So for example, it knows that the device that is connected to port 1 on the switch sent request for google.com. So it sends it to the router goes to the internet comes back to the router knows which switch, it sends it to the switch knows that the PC from port 1 requested Google, so it just sends it back to port 1. On the other hand, a hub is going to send the google.com like traffic to all the devices until the device that it asks for actually says, yeah, this is the data that I wanted, and then all of the other devices are just going to ignore that data because they did not request it. So you can see how much more efficient a switch is. Both switches and routers can be connected to one another, of course. The ability to do this increases the redundancy, which is the reliability of a network, adding multiple paths for data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there's no downtime, a small price to pay considering the alternative. Yeah, of course. So what is a router? It's a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. Routing is useful when devices are connected by many paths, such as in the example diagram below. So you can see here how routers can take data from here. It can either route it here or here, and then to this, and then to computer B, and so on. Attached to this task is an interactive practical featuring the discussed LAN topologies. Learn more about various ways. Break the LAN topologies to retrieve the flag. Okay. Let's go to the top. View site. All devices are connected to two other to create a full circle. Packets of data travel from one device until they reach their destination. One of the major flaws with the ring topology is that if a device goes down or a cable is broken, data will no longer be passed. If you hover over the middle of the network cable, you can cut it and see what happens. Boom. Packets can now no longer travel around the network, and no devices can talk to each other. Bus topology, so we already know this. Bus topology, computer 1 to computer 1. So what are we supposed to do here? Sorry. So where is computer 1 and computer 2? Computer 3. Computer 4. Okay. I honestly don't know what's required here. So is this 1, 2, 3, 4, 5, or is this 1, 2, 3, 4, 5? I don't know. So computer 1, computer 5, 3. Oh, this is 5. Okay, so 1, 2, 3, 4, 5, I guess. All right, so from computer 1 to computer 2, it would go here. No, it would go there. What the heck? Wait, let me close this. If I click view site, is it gonna restart it? Yeah, okay. So we already know this. Let's cut the traffic here. Oh, we already cut one place, okay. Let's actually read what they're saying here. With a bus topology, all devices are connected to a single cable, often called the backbone. It is sent in both left and right directions down the backbone until the packet is destroyed. A major flaw in this bus topology is that it cannot handle a large amount of data. On the next step, send as many packets as quickly as you can to try and take down the network. So from computer 1 to computer 5, and then we just spam this. Okay. The bus network is now down. Okay. All devices are connected with their own cable. Every packet is sent through the switch, which means if the switch goes down, the network will no longer. See if you can somehow break the switch. I can easily break the switch by just hammering it. This is cool. You found all the topology flaws. Thank you. So, copy and then close this. What does LAN stand for? Local Area Network. What is the verb given to the job that routers perform? Route or routing? What device is used to centrally connect to multiple devices on the local and transmit data in the correct location? Switch. What topology is cost efficient to set up? It was the bus topology. I think it was the cheapest and easiest. Was the backbone just a single wire? What topology is expensive to set up and maintain? It's the star topology, which is the most common, but the most reliable as well. You're going too fast. Yep. Right, let's get subnetting now. A primer on subnetting. As we've previously discussed throughout the module so far, which is a call to you, if you have not been following previous videos, go watch that playlist, so you can actually get as much context as possible. As we've previously discussed throughout the module so far, networks can be found in all shapes and sizes, ranging from small to large. Subnetting is the term given to splitting up a network into smaller, miniature networks within itself. Think of it as slicing up a cake for your friends. There's only a certain amount of cake to go around, but everybody wants a piece. Subnetting is you deciding who gets what slice and reserving such a slice for this metaphorical cake. Take e-business, for example. You have different departments such as accounting, finance, and human resources. So we have the internet, we have a router, we have a switch, and then we have accounting, human resources, and finance. Whilst you know where to send information in real life to the correct department, networks need to know as well. Network administrators use subnetting to categorize and assign specific parts of a network to reflect this. Subnetting is achieved by splitting up the number of hosts that it can fit within the network, represented by a number called a subnet mask. Let's refer back to our diagram from the first room in this module, which is the octets. As we can recall, an IP address is made up of 4 sections called octets. The same goes for a subnet mask, which is also represented by a number of 4 bytes, ranging from 0 to 55. Subnets use IP addresses in 3 different ways. Identify the network address, identify the host address, identify the default gateway. Let's split these 3 up to understand their purpose into the table below. So a network address identifies the start of the actual network and is used to identify a network's existence. For example, a device with IP address 100 will be on the network identified by 192.168.1.0. So in this example, it is essentially the same as if you check your router's IP address, it is most likely going to be 192.168.1.0 or 1.1. It really depends on the idea that this is probably the host address actually. An IP address is used to identify a device on the subnet. For example, a device will have the network address of 1.1. Oh, okay, so this is like the global or like the any host address. But essentially, a network address is like the start of the network, so 192.168.1, and then the last octet is going to be 0. And then the first device on the network, usually the router. If you're like in a star topology, like the default router setup, your router's IP address is going to be 192.168.1.1, which is the case in my case, I guess. 192.168.1.1 is the router that I have. And then the default gateway is a special address assigned to a device on the network that is capable of sending information to another network. Any data that needs to go to a device that isn't on the same network, isn't on the 192.168.1.0, will be sent to this device. These devices can use any host address, but usually use either the first or last host address in a network. So either it's .1 or .254. Why is the last number 254 and not 255? That's because we start from 0. So 0 all the way to 254, that's 255 addresses. So the default gateway is usually your router. This is why it's either like .1 or .254. But from my experience, most routers or like default gateways, most of them is .1, like the first device on the network. Now, in small networks such as at home, you will be on one subnet, and there is an unlikely chance that you need more than 254 devices connected at one time, obviously. However, places such as businesses and offices will have much more of these devices, PCs, printers, cameras, and sensors, where subnetting takes place. Subnetting provides a range of benefits: efficiency, security, and full control. We'll come on to explore exactly how subnetting provides these benefits at a later date. However, we need to understand is the security element. Let's take the physical cafe on the street. The typical, not physical. This cafe will have 2 networks, one for employees, cash registers, and other devices for the facility, one for the general public to use as a hotspot. Subnetting allows you to separate these 2 use cases from each other whilst having the benefits of a connection to a larger network such as the internet. Okay, what is the technical term for dividing a network into smaller pieces? It is subnetting. How many bits are in a subnet mask? Do you want to guess? Or should we take a look here? So in bits, 32, because we have 4 bytes, and each byte is 8 bits. So it is 4 multiplied by 8. That is 32 bits. What is the range of a section octet of a subnet mask? What is the range of a section of a subnet mask? What does that question mean, actually? I don't know. Let's check the hint. Smallest to largest. So I guess that's 0 to 55. Yeah, okay, so that's the correct answer. Okay. What address is used to identify the start of a network? 192.168. Oh, wait, that's not what I want. What address is used to identify the start of the network? I think this is the host address. This is what they're looking for, like the name of it. No, it is not. Oh, the start network address. My bad. Sorry. It is network address, not host address. Network address. What address is used to identify devices within a network? This is the host address. Name to identify a device responsible. This is the default gateway. Okay. So next is going to be our ARP or ARP. Recalling from our previous tasks that devices can have two identifiers, a MAC address and an IP address. The Address Resolution Protocol, or ARP, is the technology that is responsible for allowing devices to identify themselves on a network. So, Address Resolution Protocol, or ARP, okay. Address resolution is responsible for finding the MAC hardware address related to a specific IP address. It works by broadcasting an ARP query. Who has this IP address? Tell me. And the response is of the form. The IP address is at this MAC address. Now, if you're quick to catch on, you will immediately see that this is dangerous because essentially you are trusting whomever responds to this query with the information. So, for example, I want you to imagine that there are a good guy and a bad guy on the network. And then somebody says, who is the good guy? Then the bad guy says, I am the good guy. And then you're just trusting them. Similar to this analogy, you do have an attack on networks called ARP poisoning, which essentially lets you impersonate or disguise yourself as another device on the network. So I want you to imagine this, that a device on the network is trying to access the internet, and then you do an ARP poisoning attack on that network, and then you tell the device that I am the router, I am the default gateway, you should send your traffic to me. Now, this is not using ARP specifically, but if you can get that and then do ARP poisoning or ARP cache poisoning, you could make a lot of weird stuff happen within the network. So probably this is we're gonna get into this in the future, but just wanted to let you know that this ARP is important. So pay attention. So ARP, for short, is a technology that is responsible for allowing devices to identify themselves on a network. Simply, ARP allows a device to associate its MAC address with an IP address on the network. Each device on the network will keep a log of the MAC address associated with other devices. When devices wish to communicate with another, they will send a broadcast to the entire network searching for the specific device. Devices can use ARP to find the MAC address and therefore the physical identifier of a device for communication. Each device within a network has a ledger to store information on, which is called a cache. Pay attention. In the context of ARP, this cache stores the identifiers of other devices on the network. So instead of asking every time which MAC address has this IP address, you can just check your cache, like your ledger. Excuse me, lots of talking. In order to map these two identifiers together, IP address and MAC address, ARP sends two types of messages, ARP request and ARP reply. When an ARP request is sent, a message is broadcasted on the network to other devices asking, what is the MAC address that owns this IP address? When the other devices receive that message, they will only respond if they own that IP address and will send an ARP reply with its MAC address. The requesting device can now remember this mapping and store it in its ARP cache for future use. This process is illustrated in the diagram below. So yeah, message who has IP address of 192.168.1.0. It sends it to this, and then this guy says, I have IP address this, and then source MAC and destination MAC. So you can see that the source MAC here is the MAC address of this PC. It is the same as the destination MAC right here, because this device is trying to reply to this device. Now this FF, this means it is the like not a specific MAC essentially. And then the destination MAC or the source MAC here is gonna respond to this guy. So this guy can now store that this source MAC address belongs to this IP address 192.168.1.10, and that does not need to ask anymore. It just stores it in its cache, and in the cache it just checks it for this IP address, and then it does not need to ask anymore. You can just send traffic to it. What does ARP stand for? Do you remember or do you not remember? Address Resolution Protocol. What category of ARP packet asks a device? It is a query. Or is it, what category of ARP packets ask a device whether or not it has a specific IP address? Is it called a query? Or is it the message? No. Oh, request. Not the query. What address is used as physical identifier for a device on a network? It is the MAC address. What address is used as a logical identifier? It is the IP address. So IP addresses change between devices all the time, but not MAC addresses. They are literally like burnt into the motherboard. But again, you could easily, super easily spoof them. We're probably gonna get into that once we do some network hacking stuff. Now the last thing is DHCP. IP addresses can be assigned either manually by entering them physically into a device or automatically, and most commonly used by DHCP, Dynamic Host Configuration Protocol server. When a device connects to a network, if it has not already been manually assigned an IP address, it sends out a request, DHCP discover, to see if any DHCP servers are on the network. The DHCP server then replies back with an IP address, and the device could use DHCP offer, which essentially just lets it like puts on or sets its own DHCP address. So this is an offer. So I guess we can just look at this. So a discover. Hey, I'm new here. Is there anyone who can give me an IP address? The DHCP server says, yeah. Here's the offer. The request, I start using this. DHCP ACK. ACK stands for acknowledge, and we're going to get into this once we get into like protocols like TCP and stuff like that. So DHCP ACK or acknowledge is like confirmed, good to go. Okay, great. You can use that IP address for the next like 24 hours. And then after the 24 hours, you need to ask again for maybe a new IP address. I could give you the same IP, or I could give you a new one. I think this is called like a lease, if I remember the term correctly. That device sends a reply confirming it wants offered IP address, and then lastly, which is called the DHCP request. The DHCP server sends a reply acknowledging this has been start using DHCP ACK, which is acknowledged. What type of DHCP packet is used by a device to retrieve? It is a DHCP discover, I believe. No, wait. What type of DHCP packet is used by a device to retrieve an IP address? It's called the DHCP request. Is it not? DHCP. What type of DHCP is used by a device to retrieve an IP address? Is it? Are they asking about discover? Like, I would not ask. I don't know. I feel like retrieve the IP is probably the request. Send what has been offered an IP address by the DHCP It is DHCP. Is it the request? The last DHCP is DHCP ACK. DHCP. Okay, some good questions here to finish off our video. I'm gonna add the link to this introduction to LAN networking basics. This video, I'm gonna add the link to it in my video in the description in case you want to take a look at it. So thank you for watching. We are done with networking basics. The next one will be whatever, and the next one is going to be OSI model. So thank you for watching. Leave some comments, like, subscribe, all of that good stuff. I want to see that these videos are actually useful to you and it is beneficial. Let me know if you like the format of these videos or not. Give me some, like, any constructive criticism that you might have. Just let me know in the comments below. Check the description for a bunch of cool links. And yeah, thank you for watching. I'll see you in the next one. See you.